Hello and welcome to my second video on organic chemistry. This one is going to be the triple only content. So it's going to go from alkenes and understanding the reactions of them all the way through to esters and how we form them. Now I will do another video where I cover polymerization, so that will be the next one in the organic chemistry videos. So let's start off with alkenes. So we're going to jump right in. Alkenes. So in the other organic chemistry video, we've combined and triple content. We talked about alkanes, and we talked right at the end about how we made alkenes using the cracking method. Now we're going to look a bit more about what they actually are. So alkenes contain a double bond, and that will be represented in a look a bit like this. Now, carbon would like to form 4 bonds around each of them. So this one wants 4 and this one wants 4. So it will need 2 more and this will need 2 more. So it's got 1, 2, 3, 4, 1, 2, 3, 4. That's got 4, that's got 4. And it bonds with hydrogen. Now this is what we call ethene. This is the smallest alkene. You can't have methane because to have a double bond you need 2 carbons. So it's impossible for us to have methane, the smallest has to be ethene. So this is what it looks like with this double bond in here. Now that means the general formula for these is CnH2n. You don't have to plus 2 this time, you just have double the number of hydrogens compared to carbons. So you can see here 2 carbons to 4 hydrogens, and that works with any of them. Now you need to know the first 4, so that'll be ethene, it will be propene, butene, and pentene. This has got 3 carbons, 4 carbons, 5 carbons. Now I'll just do butene, I won't do the other 2. You don't need to care where the double bond goes. It can go here. It could be like this, or it could be your choice how it is. But you must make sure each of the carbons have 4 bonds around them. So this one in the middle needs another one. This one here needs 2. This one here needs 2 more, and this one here needs 3. These will all be hydrogens. I just won't draw them on. Too little space to draw these ones, but you can figure this one out, okay? Make sure they all have 4 bonds around them, and that is correct. Right, so that is what butene will look like. Doesn't matter where the double bond goes, as I said, as long as the double bond is present in there. Now, just for your information, there are things that have more than 1 double bond, and so if they've got 2, it's a diene, and if it's got 3, it's what we call a triene. But again, this does not come up in GCSE, so you don't need to know, it's just for your information. So this is what an alkene looks like. Now we need to talk a bit about how they react. So let's clear this and we'll go over their reactions. So first of all, let's talk about combustion. Again, it works in a very similar way to an alkane. You got C2H4, so this is ethene, and we're going to add it to oxygen because we're burning in the presence of oxygen. That's how combustion works, and it's going to make water and H2 or CO2. So H2O and CO2, same as before. But often alkenes have a smokier flame. So this is because more often incomplete combustion. So this is because we don't have enough oxygen in the reaction, therefore we won't be able to make CO2, end up making CO, or in this example, a smokier flame, just making C on its own, having carbon, makes it a sooty flame, and that's why we get that sort of smoky appearance. Now, this is not a balanced equation. You will have to balance it yourselves, but this is just the general equation for the combustion of an alkene. Right, so oxygen making H2O and CO2. This is complete, but you'll be told in your exams whether you are talking about complete or incomplete. As I said, incomplete, you end up with either CO or, for example, just C, and this is soot. So that is combustion of an alkene. Now we need to talk about addition reactions and how we use that double bond, because the double bond is quite an important part. It makes it very reactive. As I said in the last video, alkanes aren't very reactive. They're quite boring, and that's why we crack them to get them with that double bond, because the double bond gives it a lot of interesting attributes. So we can do something where an addition reaction occurs, and the addition reaction is where we break the double bond and it becomes a single bond, and we add two new parts to each side. So if we add hydrogen, we end up with an alkane. And as you can see, we started off with 4 hydrogens, added 2 more, and it goes into there. The double bond has been broken. It's gone from here to a single bond, and we've added 2 new hydrogens in, which should come from here. This is addition reaction, and it's addition of hydrogen. Another one could, instead of hydrogen, we could have halides like chlorine, and it will work in the same way, but will end up looking like this. Now, instead of hydrogen, we'll have chlorine. And this could be for any halide. It could be for fluorine, bromine, iodine, but chlorine is probably one of the most common ones that they would do. And as you can see, the double bond has been broken, and you've ended up with an alkane-like structure. Admittedly, this isn't an alkane. It's a dichloroalkane, because you've got 2, but it is an alkane-like structure. Right, and finally, we're going to talk about adding H2O to this. So it works in a similar way, but this will lead on to our next topic we're going to talk about. So let's just clear this. So this time we're going to add H2O. Now H2O can split into 2 parts, OH minus and H plus. Now this will add across the double bond. So the double bond will break just like before, and this time we'll have a hydrogen attached here, and we'll have OH attached to this one. And this is what we call ethanol, or in more layman's terms, an alcohol, which is what we're going to talk about next. Now this is how we form an alcohol from an alkene. We add it to water. So water will react, thrust the double bond, and it's often done in steam, because steam has a lot more energy due to the high thermal energy level. Okay, so ethanol is produced, and now we're going to work on alcohols and what they are and what we can do with them. So let's clear the board. So, alcohol. It contains an OH group. By OH, I mean oxygen, hydrogen. So, we only need to know the first 4. So there'll be methanol, ethanol, propanol, and butanol. So methanol will be quite straightforward. We have 1 carbon, because meth equals 1. And then there's our OH functional group, as I mentioned up here. Ethanol this time, 2 carbons. And this time on this one, OH. And this time 3 carbons with an OH coming off, and this time 4 carbons with an OH group coming off. So this is our functional group. I haven't drawn the hydrogens onto these. I'll just draw the lines just to save a bit of time. So this is the first 4 that you do need to know. Yes, there are other ones afterwards, but as I've said before in the last video, they're quite easy because they go from pent upwards. They use the shapes to guide you. So pentanol will have 5 carbons. Now, an alcohol does dissolve in water. They are soluble in H2O. But the longer the chain, the less soluble. So that means methanol is the most soluble, ethanol the second most, propanol the third most, butanol the fourth most, and so on. That's because this is the functional group that it very easily dissolves into water. This long chain does not dissolve very well into water. Then the longer the chain, the less likely we're going to have solubility. So they all are soluble, and that we know this because we can often mix drinks and together we make an alcoholic cocktail, for example. You mix together different water-based drinks with an alcohol-based drink, and you end up with a soluble compound. Right, now we'll move on to other reactions within it. So combustion. Combustion works in the same way as alkenes and alkanes. You have complete combustion where you make CO2, and incomplete combustion where you make CO or C. Again, these ones are slightly more smokier than your alkanes, but they still combust very easily. Next, we'll talk about adding to sodium. So alcohol plus sodium will form sodium alcohol oxide, and this is just a general formula, and I'll show you what that looks. So let's go, for example, do methanol this time. Methanol will form sodium methoxide. If it was ethanol, it would be ethoxide. If it was propanol, it would be propoxide. It just depends on which one we're using. Now this looks a bit like this. Now instead of OH on the end, we've got ONA. And sodium substitutes itself, it pushes out the hydrogen and it bonds to it. So this is a key thing when we make sodium methoxide from an alcohol reacting with sodium. So, as said, sodium pushes out the hydrogen and we get this oxygen to sodium bond. Next, we're going to talk about adding what we call an oxidizing agent. And now an oxidizing agent is something that adds oxygen in. Because there's 2 ways we can look at oxidization. Oxidization is either the loss of electrons or the addition of oxygen. So an oxidizing agent equals loss of electrons or addition of oxygen. 2 ways we can look at it, and both are pretty much the same, because when you add oxygen you generally will lose electrons from whatever you're adding it to, but is a slight difference we can look at it. Now we're going to focus on the addition of oxygen in this one. So CCOH. So we've got ethanol, and we'll add an oxidizing agent. Now an oxidizing agent has this sort of formula. You put it in square brackets O. It just because you don't need to know oxidizing agents off the top of your head, but if you remember this, you can draw this, and that's fine. And it will end up going to form a carboxylic acid, which looks a bit like this. You can see the key difference here. We've lost 2 hydrogens come off. That will end up making water, and we've got this oxygen has attached itself to this carbon, and we've got this C here. So if I put a circle around it, you see this C is this C. So the OH is still there, but this time we add it, and this is what we call a carboxylic functional group. It's a carboxylic acid. And that's what makes it a carboxylic acid. That's C double bond O down to the COH. Right, so this is how we make a carboxylic acid from an alcohol. We use an oxidizing agent here. And as I said, you draw it like this, it keeps it without you having to know what the oxidizing agent is. It just tells the examiner that you know this is an oxidizing agent. Right, next we'll go on to carboxylic acids. We'll lead into that. So let's clear this out. So, carboxylic acid. It has a COOH group, and that's how you would define it. But that, as I said, looks like C double bond OOH, and that's how you describe this as a what type of group. Now, these are weak acids. Hydrochloric acid, sulfuric acid, phosphoric acid, these are all strong acids, whereas carboxylic acids are weak acids. And this is because not all hydrogens dissociate. Don't know if I spelled that right. Dissociate, so that means that we only get some H plus acidic ions floating about, not a lot. Whereas in something like HCl, all of them separate into H plus and Cl minus, and that is our acidic ion. Weak acids like carboxylic acid, not all of them dissociate. Now, let's go on to some of the reactions. Now, with carboxylic acid, again, you only need to know the first four. You've got methanoic acid, which has got 1 carbon, ethanoic acid, 2 carbons, propanoic, 3, butanoic, 4. Again, it works in the same way, you're just adding more to the chain. So this is one of the carbons, so this would be methanoic if we added a hydrogen here. This is methanoic acid, because you've got 1 carbon. If you had another carbon here, ethanoic, 2, prop, 3, butanoic. So, when we add them to a carbonate, Na2CO3 plus a COOH, a carboxylic acid, we're going to form something called sodium ethanoate. And this looks a bit like this, and I'm just going to draw the functional group. And you will notice that just like when the alcohols reacted with sodium, admittedly that was sodium on its own, not with a carbonate group attached to it, but you will form this ONA bond, same as with the alcohol where we had the ONA when we added it to sodium. So this is what we call sodium ethanoate. Now ethanoate would have another carbon here. But this part doesn't really get involved. It's this bit, the functional group, that is the important part. So we make sodium ethanoate. We also, with this, make water and carbon dioxide. So that is the complete reaction for that. Now finally, we'll talk about the reaction with alcohol. Oh, before I do that, solubility is exactly the same as alcohols. The longer the chain, the less soluble it is. The shorter the chain, the more soluble. So methanoic acid with only 1 carbon, very soluble, easily dissolves into water, whereas ethanoic acid is less soluble, and so on. Right, so let's talk about addition with an alcohol. So we've got carboxylic acid. Let's go for ethanoic. that's ethanoic acid there. It's got 2 carbons, and we're going to add it to ethanol. So, ethanoic acid plus ethanol is going to form an ester. Now this ester will be called ethyl ethanoate. And it is the only ester name that you do need to know. You don't need to know any of the other ones, but you need to know ethyl ethanoate. And that comes from the ethyl, both parts being ethyl, or of the ethyl group, 2 carbons makes ethyl ethanoate. Let's say if one of them was methyl, it could be methyl ethanoate or propyl ethanoate, but you only need to know this one. So what happens is that we have a condensation reaction. And I will talk more about this in a polymer video I will do. But this one, H2O, is given off. And that's why we call it condensation, because condensation is water. You'll often see condensation throughout these reactions. So what happens is this hydrogen here and this HO group here will join together, and then this oxygen will join straight to this carbon, and we'll end up looking at something a bit like this. Right, now to help you out, I'm going to use numbers and colours to show you. So, this oxygen is now here. This hydrogen and these two have become water given off, the condensation part of it. Now, if I use this to show you, so this is number 1, this is number 2, this is number 3, and this is number 4. Go over here, this is number 1 now, this is number 2, but over here, this is number 3, and this is number 4. So what I've done is I've flipped this round, and you can see how it's joined. So this is what we would call ethyl ethanoate, and we have made ourselves an ester. Now esters are used in perfumes. They smell quite nice. So they're often found within perfumes. So next time you're in a shop and you smell that perfume smell, you can think of esters. And this is what we call. So as I said, the only one that you do need to know the name of is ethyl ethanoate. Okay, thank you very much for watching.